Hello, welcome to section 2.6, Limits at Infinity. You should be familiar with the following concepts from pre-calculus for this lesson. The exponential function, so here's the form of the exponential function. B is the base, which is always greater than 0. A, C, and D are constants. Polynomial division from a rational function. And what we're going to talk about in this section is end behavior, meaning what a function does as x grows larger and larger in the positive or negative direction. So we've talked about vertical asymptotes before. You've seen them in pre-calculus when analyzing a graph. Certain trig functions have vertical asymptotes, such as the cotangent function seen here. Rational functions might have vertical asymptotes. Vertical asymptotes occur at a particular finite x value. So in this case, for cotangent x, they occur at multiples of pi on the x-axis. So a vertical asymptote is a graphical representation of an infinite limit, where the y value grows without bound. A horizontal asymptote is kind of the inverse of that, where the x values are growing without bound. We're looking at the limit as x approaches positive or negative infinity, and we're seeing how the function behaves when that happens. So the most basic rational function is 1 over x. And when we graph that, we see that it has a horizontal asymptote at y equals 0. So as I travel along the x-axis to the right or to the left, I see that the graph is approaching the line y equals 0, which is the x-axis. So the reason this happens is because the denominator is growing. X is going from 2 to 3 to 4 to 5, etc. And of course all numbers in between. And yet the numerator is staying constant. So when that happens, our values are getting smaller and smaller as the denominators get larger and larger. And we say that the limit as x approaches infinity of 1 over x is 0. And notice that the equation of the x-axis is y equals 0. So that is no coincidence. Here's the official definition for a limit at infinity. So the limit as x goes to infinity of some function is some value L, or as the limit as x goes to negative infinity of a function is some value L. And that line y equals L is the horizontal asymptote of the curve. You have seen horizontal asymptotes before when you've studied exponential functions in the past. So this is the graph of e to the x. Notice that as we travel down along the negative x-axis, this function is skimming along the x-axis, so again y equals 0. So here are a couple of transformations of the exponential function. So this graph is e to the x. This dashed graph is 3e to the x plus 4. And you can see that recall what that plus 4 does is it takes the graph and shifts it up 4. So it makes sense that that is now the horizontal asymptote. Also notice I have graphed here f of x equals e to the minus x. And the limit as x goes to infinity of e to the minus x is 0. So the limit as x goes to negative infinity of e to the x is equal to the limit as x goes to positive infinity of e to the negative x. It makes sense. We're just flipping that graph over the y-axis. So you may recall that rational functions may have horizontal asymptotes. Here's an example of a rational function. And when we graph it, we see it has a horizontal asymptote at y equals 1. And the reason that occurs is, if you remember doing polynomial division, this rational function is really just the result of dividing x squared minus 1 by x squared plus 1. So when we perform that division, the quotient is just 1, and this is the remainder, minus 2 over x squared plus 1. So as x gets larger and larger, this denominator grows. So as x gets larger, we travel along the right or the left of the x-axis. This remainder is approaching 0 because this denominator is growing and growing, but the numerator is staying the same. So that's why this function is approaching 1 as x approaches infinity or negative infinity. A function can have two horizontal asymptotes. Here's an example. It's kind of a weird function. Here's a more common function that has two horizontal asymptotes. This is the cotangent function. When we have a rational function like this, where the numerator and denominator are of the same degree, there's a little trick we can do that's kind of a shortcut to actually performing the division and to find the quotient. Because, like we saw before, the horizontal asymptote is the quotient, and the remainder is what's going to 0 as x goes to infinity. So we don't have to go through the polynomial division every time. We can use this shortcut. So since x is going to infinity, and minus infinity for a horizontal asymptote, we can perform this trick of multiplying the numerator and denominator by 1 over x. We don't need to worry about x being 0 because it's going to infinity and negative infinity, so we can do this. And when we multiply the numerator and denominator by 1 over x, we see that we have 5 over x plus 4 divided by 1 plus 3x. And as x grows to infinity, these two denominators get large. The numerators are constant. So these two values go to 0. And this gives us a limit of just 4 over 1, or 4. The same thing here with x going to negative infinity, of the same limit. And I can see then that the horizontal asymptote's y equals 4. The vertical asymptote will occur for a rational function at the 0 of the denominator if it's not a whole. We can see this is not a whole because x plus 3 would be a factor of the numerator and denominator if it were. So we know that the limit's going to be infinite at a vertical asymptote. But we need to check the direction, because recall that vertical asymptotes can split. On one side of an asymptote they might go up to positive infinity, and another they might go down. So you want to look at close to the asymptote on either side of it. So for x values greater than minus 3, if I, let's say, put minus 2 into this function, I would get a negative numerator and a positive denominator, which gives me negative. So I know that on the right side of that asymptote, it's going to minus infinity. And if I plug a value in close to minus 3 to the left of minus 3, let's say minus 4, that would give me a positive numerator, a negative numerator and a negative denominator, which would be positive. So the limit as x approaches minus 3 from the left gives me positive infinity. You'll also see problems like this where you're supposed to find certain limits from the graph. So the limit as x approaches negative infinity, you can see it's approaching that horizontal line, y equals 2. The limit as x approaches positive infinity, you can see approaches the x-axis, so that's the line y equals 0. The limit as x approaches minus 1 from the right, so here's minus 1. As it's approaching it from the right, it's going to positive infinity. As it's approaching minus 1 from the left, it's going to negative infinity. So again, those vertical asymptotes can split directions. And it also has a vertical asymptote at x equals 2. So here's a type of question that you're going to see that I want to warn you about, because this is the type of question that has a very different thing for the student to do if it's in WebAssign versus on a test. So to sketch the graph of a function with all these given conditions. So in WebAssign you would just choose a multiple choice graph, but on the test you're going to have to really draw a function. So you want to make sure that you do these problems on paper when you're doing your homework. So one way to do these problems is to start by drawing the asymptotes kind of as a framework for your function. So if you look at the limit as x approaches 0 of f of x is minus infinity, so that's telling you that x equals 0 is a vertical asymptote. And these two limits at infinity are 4 and minus 4, so those are telling you that you have two horizontal asymptotes. So that's your framework. You're also being given these 2 points. So the next step would be to plot those points so that you know that the graph has to go through those points. That helps you kind of guide how you bend your graph. Then notice that the limit as x goes to 0 of f of x is negative infinity, so that means that the graph goes down the y-axis on both sides, coming from both directions, because the two-sided limit's negative. And then finish the graph by skirting along the horizontal asymptotes, making sure you go through those points that you've already plotted. Make sure you don't violate the vertical line test. You need to draw a function. So with limits at infinity, not all but 2 of the same limit laws still apply. And plus we have this new limit law. So the limit as x goes to infinity of 1 over x to the r, where r is a rational number greater than 0, is just 0. And the same with negative infinity if x to the r is defined. So I'm going to come back to this example in a follow-on video because it's pretty involved and I am running out of my 15-minute limit with my recording program. See you in a minute.